There we go. Now I'm unmuted. Hopefully everybody can hear me. Want to welcome everybody today. We have the binging of my clock that I forgot to stop here in the background, but it'll be over in about 12 bings. So I want to welcome everybody today. My name's Gary Smith. I hope everybody had a really neat Christmas and time off with their families this year. Please again excuse the grandfather clock. Today we're going to be going over a really important subject in my mind, which is during this WMDA Lunch and Learn, which is deposits and diagnostics. It is a very, very important subject in relation to getting the answer on the car. I do have one question here I just want to check on real quick, just to make sure we don't have an audio issue. Okay, good. No, we're good. So again, I want to welcome everybody, get this out of my way. Welcome everybody to the webinar today, to the WMDA Lunch and Learn session. Now, those of you technicians that are on with me today can very easily identify with what we're going to be going through here. When we're talking in terms of difficult deposit-related drivability concerns, we're talking about the real pesky ones that are giving us trouble out in the field. For example, the ghost lean codes that are sometimes near impossible to solve or find. We're talking about the intermittent misfires. We're talking about coked up turbos. We're talking about catalyst efficiency codes. All of that stuff we're going to cover today. Now, this is a very condensed version in a 45-minute to 1-hour form of a 4-hour class on this same subject, okay? So there's only so much information we're going to be able to pack into this 45 minutes. But I do want to let you know there's enough information here that I'm going to just keep rolling here and teaching, okay? And the reason for that is I don't have a moderator working the questions bar for me. I will stop in the middle if I see any questions and try to answer them, and then we'll have a question and answer period at the end, an open mic question and answer. So if you'll write down or hold your questions until then, I'm going to just keep firing away here because we have a lot of stuff to cover. Now, first time out with the brand new laptop, so please bear with me if I fumble and stumble a little on the presentation here, but I want to basically cover the theory behind what we're going to talk about today. The fuel control system on the car, guys and ladies, is something that is designed to within the parameters of the engine that it's built around. And because of that, all of the mapping and the parameters and the code setting criteria, as well as the truth tables that all the sensors look up, are set by the manufacturer. Now, this is an important thing to start with here because I want to introduce the theory of baseline diagnostics. Okay, baseline diagnostics is something I've been using and working on for 20 plus years, especially when it relates to finding and solving deposit related issues using my scanner and my scope, my equipment. And the baseline theory assumes that a new car with a clean engine that's never burned a gallon of gasoline or a quart of oil is going to run at a certain baseline. For example, if it's a 3.5 liter V6, there's a given volumetric efficiency in that engine that's loaded into the fuel maps. Now consider as we build up carbonaceous deposits all over that engine, and we're going to cover the main 4 deposits and where we're seeing them in the vehicles today. And kind of talk about how the deposits, as they build up, create adjustments to the baseline and the fuel control strategy. And guys, I'm going to tell you, this is a really important issue when it comes to things like mass airflow plausibility codes and ghost lean codes that you can't find. This baseline theory can really begin to help you to dial in on these deposits as being the problem before we're spending 2 or 3 hours or 2 or 3 days of diagnostics in the electronic side of the car, or in the case of sometimes flat rate panic heating up the barrel of that parts cannon, right? So to me, this is a hugely important subject to really key in on. Now, baselining basically provides the technician with a controlled fact-based diagnostic angle that utilizes what I like to say is repeatable scan and scope data, okay, and physical testing data methodology to help you guys determine the cause of a drivability issue. Basically, in the world of GDI cars, okay, these vehicles owners are presenting at our shops with a couple of really weird code, no code related issues that are very difficult to solve. One being a poor fuel economy complaint, and one of the most common on the GDI cars is a lack of power. And we're going to cover that one in pretty good detail here. Excuse me. So basically, the new modern day GDI engines are going to degrade in performance much, much faster than a typical old multi-port car would for a number of reasons. One of which is the tolerances within the engine and how they're built. Okay, the GDIs and the small turbocharged, 4 cylinders and even turbocharged 6 cylinders are very tight tolerance engines, much more so than the old multi-ports. But then the fuel control systems are faster too. But the real issue that we're going to drill in on today is these fuel and oil carbons that are building up in these engines are completely whacking out the OBD2 data over periods of time if nobody is aware of the buildup in the car and nobody's looking for it. I know it's quite common to be selling induction services and carbon cleans on vehicles today. That's not a mystery anymore. It's not a snake oil thing anymore. Everybody knows that chemistry and physical carbon removal is necessary in these cars, okay? But diagnosing some of these ghost complaints can be a real issue, and baseline theory can help us to kind of unlock that. So, why use baseline? Well, here's the question for everybody in the audience, okay? How does one quantify a poor fuel economy complaint or a low power complaint when there's no associated DTCs? The customer is not, we have to assume that the customer is not bringing that vehicle in to the shop to waste a day and get rides to and from work and picking up the kids and all the stuff that they have to go through to get their car to us with a complaint like that if they're not feeling something. Well, the problem is that you or I get in that vehicle as a technician and we go belt the gas and get down the road in the car, and it seems to want to rip the tires loose against the traction control. So we come back to the shop, look it over, check it for codes. There's nothing wrong with the car, and it seemed to have all kinds of power, so we do a no condition found. But yet that customer's back 3 or 4 weeks later going, you know what, guys? I'm telling you, this thing just doesn't have the guts it used to. This is something we can see with baselining if we're keyed into how it works and what we should be expecting, okay? Now, all of these things that we have on this screen can be good reasons to baseline a vehicle, right? So let's continue on and see if we can figure out a different approach to how to look at some of these drivability problems. So here's really the theory behind baselining: what the car should be doing when it's clean and new versus what it is doing now in front of you at your altitude. And hopefully I'm going to get back to that altitude argument here before the end of the class, because it's a very key one that makes baselining even more important for regular diagnostic approach, not just looking for deposits. What I mean by that is let me just cover it now so I don't forget. If you consider the altitude factor here, it is the number one and only reason why a manufacturer does not and cannot give you a very specified number for any given sensor while the engine is running. And the reason for that is it's the same system at sea level as it is at 7,000 or 9,000 feet in Colorado or 5,000 feet. Okay, and so what happens is the manufacturers have to give us a diagnostic range when we're looking at these codes. For example, the mass airflow sensor range, acceptable range is, 3.0 grams per second up to 15 grams per second at wide open throttle. Well, if you look at those sensor ranges during any diagnostic, never mind just carbon or a problem being caused by carbon, that's significant, okay? Because we go by diagnostic problems all day long in this business because of those specs. Is the number between this and this? Yes, move on to the next stage. My friends, I'm here to tell you, that's the fastest way to broom a car with no condition found and go right by the problem. So baselining is basically what it should be doing versus what it is doing. And as in the independent aftermarket, we don't have brand new cars per se to go pull off the lot and get those readings. We learn our baselines through before and after cleaning and looking at the data before we clean the car versus after we clean the car. Assuming that we did get down the deposit down to a manageable level, we're going to call that our clean baseline in the independent aftermarket, and then start to build some diagnostic thought and some diagnostic data from that information that can really help us when we're going after these weirdo problems, right? So we can use the baselining technique with scan data only, or we may choose to employ an engine modeling physical testing system, such as a scope and a set of pressure transducers, to look at the dynamic in-cylinder waveform, check for valve leakage, do all kinds of cool stuff, which I'll cover in brief form here. But baselining is a very important thought. Now, if we take that baselining thought process and roll it into the industry issues that we're seeing directly related to these carbonaceous and oil deposits, and believe me, guys, in the GDI realm, the oil deposit, the ring control, the oil control via the piston rings becomes a far more important argument as the start and the rapid degradation of the engine occurs based on carbon loading. It all starts with the rings in a GDI car. Think about it. Higher compression engines in all cases with GDI. If you've got higher compression, those rings are having a tougher time, the light tension rings having a tougher time staying healthy and alive, even more so than in a multi-port car. And ring control was a big problem in multi-port cars, as we well remember. So it's not just about fuel carbons and valve deposits here, okay? The start and the rapid buildup of those valve deposits often occurs because of a loss of oil control on the piston rings. So we're going to key in on that too. But look at these things that we have on the screen right now and tell me that every single one of these aren't things that we do battle with, see, or diagnose every single day in our shops, okay? Every single day we're seeing misfires, lean codes, everything you're looking at here, converter codes, injector failure, high pressure pump failure on these GDI cars. Every single piece of this really comes back to proper lubrication, proper maintenance, and the reduction of carbon. What you're going to see here as this unfolds is that one of the big considerations, the biggest consideration in my mind, excuse me, for why these engines build up fast is the drive cycle of the car. What I mean by that very specifically is a customer, let's say that, for example, in this area might be what I call a short tripper, okay? And what that means is he's driving 5 to 12 miles each way to work every day. And worse than that, he's sitting on the beltway. And because of that, that car is what I call a short trip, stop and go city driver car. Now in the GDI realm, there is nothing worse for carbon buildup or carbon problems for a GDI or a high pressure diesel for that matter than extended idle times. So when you think about the number of GDI vehicles that are sitting in traffic in our areas, okay, going very short trips to work, these are the customers that are in deep, serious problems drivability wise with these issues, okay? Because the carbon in all cases is going to move baseline data in our OBD2 system and create the adjustments and the issues that you see on this current screen. Meaning we know as soon as we throw carbon into the mix, and move or upset the tumble and swirl of that charging of air into that GDI cylinder, we're going to start to affect airflow, air and fuel mixture, and burn characteristics in that cylinder real time. Because all of these GDI cars, it's not like the old days in the 70s where they plunked a piston in a hole and put a high tension ring in it and had it go bang, bang, spark, spark. You guys know, and I know, that it's way more complex from a mechanical movement and engineering standpoint with the valve phasers and everything else, the cam phasers that we have. Everything put into the equation here means we've got an upset in the way that car is running, okay? We create lean conditions. The injectors then have to increase their count, or the air side needs to adjust to compensate for that. All of this data is easily identified and readable if you use what I like to try to do for myself. I'm just going to share with you what I do for myself and have over the years, is a repeatable process, meaning I'm going to look at the same 5 or 6 data PIDs every time I go after this. Why? Because the more I look at the 5 or 6 data PIDs we're going to be talking about today on every car, regardless of what size engine or who makes it, the more I start to build a picture for what's right and what's wrong in that diagnostic process. And that, my friends, is really powerful if you want to save time messing around for useless range style specs on all data all day. I'm all about fixing cars. That's why this is important stuff to cover. Okay, but look at the issues on the screen, especially the bottom one, because as this GDI builds deposits, horsepower really rapidly decreases for a number of reasons. Okay, now, what are the fuel deposits we're after? This is important to quantify and know what they are and where they're coming from. And once you really start to get a picture of this, then one can understand why the short trip cars, the short trippers as I call them, are getting in real trouble, because they are not getting the time, the heat, and the mileage to burn these fuel and oil carbons out. They're just sitting there stacking up in a very close tolerance engine. And so the time to fouling of that engine is 1/3 of what it used to be in the multi-port world. And what I mean by that is that you can get a lot of these GDI turbo cars that are short trippers, guys, in drivability problems that are creating check engine lights and in some cases having the car towed in less than 10,000 odometer miles from new. All right, now, what's happening here? We've got 4 kinds of deposits. We have the gummy deposit, okay, which forms basically from the oxidation of the fuel in the tank. The mixture of oxygen, sulfur, heat, and moisture is going to start to break that ethanol fuel down. I've got a slide or two for you here in a minute on that shows you that process in a bottle so that we can see how that breakdown works and what it's doing in that fuel tank. Now, as that substance mixes with the metals in the fuel system, the feed pipes, the return pipes, the injectors, the rails, that oxidative process, that oxidation process is taking that yellow gummy deposit and turning it kind of a brownish red from the actual oxidation or rusting going on inside of the fuel system, which does occur for those of us that have pulled these fuel pump modules out of some of these cars. Now, the varnish deposit is the next stage after the gummy deposit, and that is going to be a very important stage for the injectors. You'll see that in another slide or two. The varnish deposit is the one that's going to put the wear and tear on the injectors, okay? And I'll show you why that is in a second. The hard carbon is the one that we think about and know and love. That's the chunks of lovely yuckiness up on those intake valves, also coating the piston crown, valve reliefs down along the piston rings, coating up those ringlands. Big factor here, okay? But a big one for GDI cars that's not discussed or talked about much today, guys, is the soot deposit. And the GDI vehicle soots much more heavily than a multi-port car does because of the high pressure injection. So it soots very similarly to that of a high pressure diesel. Now, considering that, we've got some issues post-combustion that can creep into these vehicles, such as switch time codes, slow O2 and air fuel ratio sensors, and then of course, depositing on the catalytic converter itself, eventually leading to a clog, right? So if you think about these deposits in terms of gummy deposit, varnish deposit, hard carbon deposit, and soot, now we've got a picture of what is cycling its way through the engine right now. The next slide here, I'm not going to spend a ton of time on because we don't have it today. I do spend a ton of time on this, or a much bigger amount of time on this on our 4-hour class. There's just not enough time to show you this whole thing. But what I do want to point out is that, let me see if I can get my little pen up here. Whoops, here we go. Here we go with the unfamiliarity. Bear with me 1 second, please. There we go. Sorry about that. Like I say, just pulled this computer out of the box last night, so it's a little gnarly running it today. Anyway, big thing I want to point out on this screen, okay, is the, oh look, there's my pen. Maybe I can grab it. Bear with me 1 second, guys. I want to see if I can get a pointer up here without killing this slide. Oh, look at me go. All right. Big thing I want to concentrate on, guys, is right here in the gasoline band, okay? In the gasoline band, this distillation process, okay, is going to be a cause and a creator of the oxidized or fast oxidizing fuel that we're seeing today in use, the E10 ethanol fuel. Why? Because there isn't enough of this 8 carbon chain gasoline to go around. So what they've been doing on EPA reformulated gasoline rules, you've heard of the tier 1, 2, and 3. You've heard of reformulated gasoline, I'm sure. But the EPA has us doing reformulated gasolines, which are actually created, the fuel base for which are created down here. Now, just quickly, the crude oil barrels, 42 gallons traded on the market, excuse me, and then it's going to get boiled off. If you look at this boil off temperature, it's really hot. It's like 1112 degrees Fahrenheit. And what they're doing with this baffling is they're keeping the heat down so that it's cooking and cooking the cokes and the heavy elements out of that crude oil. Well, because of the shortage and the inability to use this gasoline that's naturally distilled at 8 carbon chains, what RFG rules have us doing is cracking fuel down further in the barrel into the thicker base to get the base for the fuels. Now, let me just explain really quickly how that works. What this hydrocracker, this cracking unit's actually called a hydrocracker, and it's cracking with hydrogen. So one of the first problems with this process is we're having a precursor to a water molecule distilled into the fuel base by virtue of how it's being made by the cracking. Now, the thing I want you to pay attention to is that we are cracking very heavy elements of that barrel. For example, you've got 36 carbon chain lube oil stocks here and 44 carbon chain heavy gas oil. For those of you that were in the military, that's bunker fuel, really, really thick, nasty oil, okay? And that lubricating oil and heavy gas oil is being cracked, okay, to bring the higher elements of that base oil up. Now, what you'll notice is that the base comes out of the fuel, the cracking unit here, travels up the pipe. Notice that pipe comes above the gasoline band and into the reformer, hence the name reformulated fuel. Now, this is where the higher elements, the more volatile or you know, high evaporative or lighter elements of that fuel are then blended with the heavier coked cracked base, okay? So that at the end of production here, what we've ended up with, if we draw a line from here, considering this pipe, and here, considering we're in the gas and naphtha band, is that we're building an average manufactured 8 carbon chain gasoline. Now, that becomes really significant, specifically for the purpose of, oh, let's get that out of there. Hold on, I got to change my arrow back. That's important specifically for the purpose of what I'm going to show you next, which is the gummy deposit. Sorry about that delay. Normally, I'm not this fumbly with my presentations other than the brand new computer. Other than that, I'm feeling great. Okay, so the gummy deposit, big effects from this process, okay? And it starts with that water molecule. Now, they form from oxidation of the fuel, heat, oxygen, sulfur, and moisture mixing in the fuel tank as that car is driving around, right? Now, here's the important thing. This is the visual on the gorilla snot or the deposit that actually takes place. Now, the reason that we did this in this form and in a clear bottle was to show, we built this at a friend of mine's Ford dealership up in Canada, actually, right? And the purpose was to show the customers and the technicians what's really going on in that fuel tank over time. Now, think about this for a second. Okay, the stuff that you're seeing on the screen, for example, here, okay, is the E10 ethanol blend. This yellow substance with the little oxygen bubbles pulling up here toward the vapor space is the actual, what I jokingly call the gorilla snot, but that's the actual yellow paraffin wax that is oxidizing and being pulled out of the fuel. Now, what these oxygen bubbles are trying to do is get the deposit up here so that the oxygen bubbles can release into the vapor space. But as this fuel sloshes around in the tank, this oxygen's being infused, it is reacting with the water molecule, it is stripping the paraffin, and it is slowly pulling it to the top. Now, the big thing to remember here is two things, guys. If you consider this area right here to be the bottom of the fuel tank, okay, because this fuel is always going to ride right at the water interface, and there always is a water interface in the tank, even if it's very minor, okay? But think about this. This is where your sock is. And the point I want to make here is that once this deposit forms in the tank, it is now going to pull all the way from the top of the tank supply all the way to the bottom in the sock, as you can see here. There is no break from it. Now, let me be very clear about this deposit. This deposit that you're looking at on the screen, the E10 on the right side of the screen, and the E85 sample that we did, both of these fuels had only been sitting for 5 days. And we built them by chemical formula, by a lab formula that was given to us to oxidize the fuel in a natural form, the same way it would be in a vehicle. Part of that included shaking the bottle a couple times a day as if the car was driving around. Part of it was the light, meaning the heat hitting the bottle. So this is real deal. And what ends up happening here is that at 5 days, we have this growth right here. Look at the growth in the E85 because of the alcohols involved, stripping that fuel even faster. This is the reason, the visual reason, why we can understand why ethanols have to be blended at the terminal level and cannot be put in at refinery, because if they were, the fuel would be going to this before it ever came out of the mobile station tank and into the car. No bueno, right? So this is what we're after. Now, this is going to create probably 80% or more of the depositing that's going on in that vehicle. But the second point I want to make before I flip the slide is that this problem will not be as bad for folks that are running a tank and a half of gas through their cars in a day, like I typically do, or in maybe in 2 days. In other words, if you're turning that fuel really quickly, you're not going to get as much of this. It's still going to be there, but it's not going to be growing as much of it. This goes right back to drive cycle, and not only the heat and carbon, burning out of the engine, but how much of it is being made. Because if you're a short tripper, you might have that gasoline in your tank 2-3 weeks before you fill up. That car is getting decked with that deposit. We need to understand it, treat for it, know about it, and then put baseline theory together to go look for it in our scan data and help get it out of the car. but that is the significant visual that you need to see to understand the drive cycle aspect of it, in addition to the heat of the engine. Okay, now, this is an old tank. We don't see the metal tanks that much anymore, but I did capture this out of an old Cadillac just to show there really truly is lots of rot and corrosion going on in that fuel based on the heat cycling and the mixture of oxygen and water. Now, this is one of the main reasons why they're A, doing plastic tanks, and B, plastic fuel pump modules. But you have to think about all of the metal, steel, and aluminum that it still does contact within that fuel system. Okay, we're still getting some corrosion, not anywhere near what we did in the old days, but we still are getting a lot of that fuel breakdown and problematic clogging of the injector screens. So that's something to watch out for. Now, this is where I said we would have a good argument as to how the deposits are loading into the engine. Now, if you think about that, the gummy deposit picture I just showed you, one of the points I didn't make about that gummy deposit is that it is a thick liquid paraffin wax in the form it's in, which what that means is it will come right through a filter substrate, whether that be a sock or a permanent tank filter, and even paper filters. It will move the deposit through that. Why? Because in that paraffin form, it's not like a grain of sand or dirt that the filter can catch. It's going to come through the screening, and it's going to start to load itself right here in the tops of the fuel injectors. Okay, and this is where we're going to start to see a problem. I've had several of these vehicles apart, and if you take these injectors out, in a lot of these cases, once they're badly fouled, and you just take a white rag or even a white piece of paper if you don't have a white rag, and you flip those injectors upside down and just knock them on the bench, you will be shocked at what comes out of them, at what it looks like. Some of them look like pink salts. Some of them look like rusty little flakes of rust. Some of them look like white salts. I've seen some white salt looking stuff on Hondas. Okay, guys, there are problems with this. And when we have these ghost lean codes that we're seeing, where you're smoking the engine and all kinds of crazy stuff, your fuel pressures are good, you're scratching your head, you're like, what the heck is going on with this car? I've caught many of them in the last couple of years where you pull that rail out and flip those injectors over and tap them and clean them, put them back in and run a rail service on it, car straightens right out. I've also had others, like a Chevy Cruze we had last week, that had a ghost lean code that went through thousands of dollars worth of work at 2 dealerships and an independent shop. And it turns out all 6 injectors were badly fouled like this here in the top, and a fresh set of injectors straighten that car right out. And I'm talking, this is after they threw PCMs and programmings and all the bulletin stuff at it. These guys went nuts figuring this car out, and it was diminished flow through the injectors. So this is where we're going to get the gummy deposit. Now think about this. We're entering the top of the injector, even in a GDI, in a much cooler spot of the engine than we are at the tip of the injector. So this is where we're going to see the actual deposit begin to change physical states. Excuse me, a little scratchy throat today. Now, if you consider the yellow to be the fuel here, and you look at how this fuel is coming through the injector, we're realizing we have a wet solenoid here, okay? As such, as we get further down in the injector, the heat factor starts working on it, and the friction factor from this pintle pulling up and down rapidly, okay, right here. Now, as that's happening and as the heat is working on this gummy deposit, it begins to form a varnish. That varnish will start to restrict the inner body of the injector in the middle of the screen that you can see here. Whoops. All right. And what's going to happen there is we're going to start to just get more heat and wear and resistance on that injector solenoid. When we want to think about how an injector winding burns out, this is the process that begins to get it there if we take normal wear into consideration and we're not looking at an open circuit winding failure, okay? But even sometimes when we are looking at an open circuit winding failure, that's the beginning of the cause, because it's been working on it for so long and everybody's like, oh, you don't have to clean these systems anymore. Yeah, no, you really do. Okay, because this is where we're getting a tremendous amount of problematic wear in the GDI injectors. And there's so much finer tolerance and so much higher current injectors. Some of them fire up as high as 80 or 90 volts, that it just can't hang like the old days with the low pressure injectors. Now, to move down here, when we talk about GDI going directly into the combustion chamber, this is where we get real quick drivability fouling on short trip cars that are building carbon quickly. And that's because as this tip falls down here, okay, and the fuel gets restricted, most of our GDI injectors will either have 2, 5, or 8 injection holes, depending on whether it's spray guided or spray directed engine, or simply just a Bosch system, okay? Either way, those are going to be very seriously sensitive fine tolerance injectors. Now, the problem is when we start looking at the fouling of the carbon from the fuel side to the oil side, the intake side, now we can start to put baseline to work and begin to put an argument together for looking at the data on the air control side and looking at the fuel control data to see if we can see these deposits building up in the engine and affecting it. So the other area that we really get a lot of problems in the depositing area is in the variable valve timing. We just had a Chrysler last week, a Jeep, that actually had a problem with the phaser loading with sludge. And so what was happening is after the PCM would release the phaser to go back to its normal timing position, it was hitting a wall with that impacted sludge, wasn't returning, excuse me, and it was setting trouble codes, and it was a little bit of a diagnostic issue for the shop. Now, the screen that you're looking at here is actually the pressure waveform that I use to diagnose a lot of these concerns from the non-scan tool side, from the physical testing side. Why? Here's what I've learned as a support tech, guys. I have tons of people calling me with these issues day over day, week over week, month over month. And all of the work has been done in most cases with that scanner to try to get that tech to the answer, as well as in the case of maybe a misfire, a coil swap here or there, or this part or that part. And what I'm learning with these gas direct injected cars is if you consider the depositing coming from the intake side and following that valve, in all GDI applications, the swirl and tumble that's engineered into the way that air loads into that cylinder is now affected. And gas direct injection cannot work with properly or burn properly, cannot, with a capital C, cannot, with carbon fouling over that valve, because the minute you interrupt the tumble, you now interrupt how that tumble is controlling the rich ball of fuel in the lean cycle that's supposed to be held right up by the spark plugs so that the cylinder lights evenly. The second we get that carbon buildup around the valve, all bets are off there. Take that argument, intake, okay, to the rings. Now the rings are sticking and diminishing in their efficiency to seal the compression. Now we're getting blow-by gases, rapid oxidation of the oil, transfer of fuel into the oil base, and we are breaking down the oil faster. What's the detriment there? Everybody out there is comfortable, including shops in a lot of these day and ages, with this 10,000 mile oil change interval, or waiting for the light to come on in the car. Listen, when we have a vehicle that's 40, 50, 80,000 miles, the rings have started to degrade, and we're now having a serious drop in compression. And when I say serious, in the baseline strategy, we just did one last week online using carbon removal chemistry for the rings, and pulled back an average of 36 pounds per cylinder. 36 pounds per cylinder, guys. when you have customers that are coming in talking about lack of power and you can't find the problem, you need to start checking that compression. One of the beautiful things about using this waveform is we've got our peak running compression right here. Okay, we've got valve exchange or gas exchange area down here. This yellow line, if I look across the bottom of this intake pole versus the bottom of the exhaust pole, is pretty close to the same line, right? And this is where we're going to check for valve leakage. Here at the bottom of this pocket right here is where we're going to check exhaust camshaft timing. Now, when it comes to variable valve timing, this is an incredibly important baseline tool to understand what's going on with those cam phasers when they're being commanded on and off. And this is a great way to find valve leakage creating intermittent misfires, as well as cam timing problems. Intake cam timing is checked over here. Let me see if I can get my little cursor back right here. Okay, so intake cam timing, exhaust cam timing. This is back pressure in the exhaust. Guys, if we have a clogged exhaust, this comes way up in a hump. This is a very important waveform to use today in gas direct injection cars, especially in the age of deposit problems creating oil pressure issues with cam phasers, chains, jump timing chains. Guys, I cannot stress enough. Right here, this waveform on the screen is typically over 70% of the case fixes that call into me regarding these deposit-related problems, ghost misfires, lean codes, math plausibility codes that'll be set. Man, you'll drive yourself nuts looking for sensor problems with that mass plausibility code, and it's a dirty intake. We can see it here, right? This is, to me, passionate stuff. We got to get guys in the habit of using this stage 2, step 2, to go after these deposit-related problems, the leakages, the hard stuff that we can't find. Why? Because when the support call comes into us, guys, all the scan tool magic has been done on that car, and it's this or some sort of modeling of that engine that allows us to actually diagnose it and fix it. Because your scan data is one thing, but that sometimes requires a tremendous amount of lookup work. And then again, you're dealing in ranges, so you're never really sure whether or not you're seeing the problem or whether it's normal. And this is what leads to misdiagnosis. So, guys, scan data, we're going to cover that as we come into the end of the class here. And scope. The mechanical fixes we're catching today, I'm going to repeat it, are 70+% of gas direct injection drivability. And we're not catching it with a scanner, okay? We can, it just requires a lot of specs and study and, to me, wasted time and misdiagnostics, okay? So let's go through, we talked about baseline theory, all that stuff. Here's what I want to key in on as we go to the final argument and slides. All right, now, again, baseline, clean and new. What was the data doing before deposits started making fuel trims and throttle motors and injectors move away from their baseline? What was the vehicle doing versus what it is doing now? Make a comparison. What do we need to establish? Where is the vehicle's current operating data as it sits in front of me with a problem, or even pre-cleaning? Maybe I don't have a problem and I want to apply baseline theory quickly and effectively. What does that mean? Warm the car up before your induction service. You're going to capture the 5 or 6 data PIDs I'm going to leave you with today. And then you're going to just take 5 minutes after the service, which sometimes we have to do anyway because we set a check engine light or something, right? 5 minutes, warmed up after the service, pull the data again. Now we've got an idea of what clean versus dirty looks like. And if we do that over and over using that same data set, man, we have a very powerful diagnostic tool there. Now, let's get down to our slide. Now, what I want to do, if I can do this again without killing my slide. Bear with me a second. All right, is what I want to do is I want to take us from the tank, okay, where we have this gorilla snot growing that we were showing you. And remember that gorilla snot is in a column, but it's also kind of laid up on the insides of the tank where it's sloshing around. So there basically is no escape. It's either pulling through the sock or it's being recirculated by the fuel sloshing in the tank. So it's coming to an injector near you is what I'm getting at, right? Now, again, we're going to let that deposit cruise right through the filter because it is a thick liquid, not a grain of sand that the filter can catch. And then we're going to load some of that depositing in the tops of the injectors. Now, I want to just kind of flip-flop back and forth on baseline theory and make my arguments right here on this slide because we only have a few more minutes to get this wrapped up. And this is really important to start to study baseline theory and how it can help your diagnostic. Now, what do you guys, since you can't answer me, I'm going to answer my own question, but what do you guys suppose is going to happen as this stuff starts to slowly build up and restrict those injectors over time? Well, Gary, the obvious answer is the long-term fuel trim is going to adjust or add fuel to compensate for this restriction right here, okay? Now, that means long-term fuel trim is an indicator of the movement of the engine. Now, let's take away the total fuel trim diagnostic equation for a second, just for this argument. I don't necessarily want total fuel trim in this case. I just want to see the long-term trend. Excuse me. Now, so I'm going to add fuel, okay? Now, let's remember we've got varnish deposits working on these injectors, and then let's concentrate on good injector spray versus fouled injector spray. This is another area that we can't physically see as the engine's running that becomes critical to consider. Because if I have this going on and the spray is not atomizing nice, it's spraying against the cylinder wall, I've got a partial or full misfire in that cylinder, but I've also got a rich condition, okay? Now, if I've got a rich condition because it's leaking or dripping or dribbling, okay, I might have long-term fuel trim subtracting fuel on this car. Either way, if I'm going after a drivability, I need to know what that is when I'm looking at whether these deposits are affecting the vehicle or not. So long-term fuel trim is a big one. Okay, now, if we, let me see where I am. I can hardly see that dot. There we go. If we consider and move this deposit into the intake runners, and believe me, guys, if you've gone down in these intakes, especially the really bad ones, with a borescope, you know, not only are we getting that deposit on the valve, but worse than that, the intake runners are becoming infected with that carbon deposit, and it's growing on the intake runners right where the air charges down into the valve. Those of us that have looked with a borescope on car after car after car, you can see an almost Grand Canyon-like buildup of carbon. Looks like peaks and valleys all through the intake. And what the valleys are is simply where the main airflow charge is actually flowing. The carbon's going to build up around it. As this occurs, okay, and in addition, we foul this baby over here, okay, with more carbon, okay, now we're interrupting the critical air swirl that is supposed to be going on properly in this cylinder. And what I mean is the control here that's engineered into this tumble and swirl equation that holds that rich ball of fuel cannot be understated on a GDI car. Let me give you guys a hint. The first sign, the very first sign, and you can take this to the bank because I've seen it hundreds and hundreds and hundreds of times, no joke, hundreds of times. The signal that you can take to the bank with any gas direct injection car that it's starting to get into trouble with this right here is a idle shake at idle. Okay, with your foot on the brake, car and drive, assuming it's not a Honda Accord with bad fluidic motor mounts, okay, that idle shake, it's purring at idle. And if you just crack the throttle open, I'm not talking rev it against the gas pedal, right? Not brake torquing it. But if you have that idle shake and you just crack the throttle and it smooths right out, you better pay attention to this data, guys, because this is your problem, okay? And I've seen this so many times. That's why I say this is a tip or trick of the trade, you know, that you can take it to the bank. If that thing's got a rough, raspy idle shake and it's a GDI car and it's got mileage, get into your baseline data, figure it out, because this is going to be creating it. Now, so we're restricting the intake. Now, guess what, guys? The worse this gets, okay, on the high mileage GDIs, this is where we get into MAF plausibility codes, okay, that are not calling a bad sensor or circuit problem. It's just saying this mass airflow data does not agree with this truth table. What's going on here? As we build up these ridges on the intake and we move the carbon higher and higher, we're restricting the volumetric efficiency, if you will, of that intake. And we're messing with the amount of data that, or air rather, that's coming through it. And therefore, we get that MAF plausibility code saying, hey, my truth table says this much air should be coming through, only this much is. Something wrong, flag a code. Right now, this is where I want to really key in on baseline data and how to fix or find some of the much harder problems, meaning no code, poor fuel economy complaints, and low power complaints. Pay attention here, guys, because here's where it is. Think about what we've got here with the throttle motor. Now, we don't have an IAC anymore, and if we do on an older car, I'll make the same argument here in a second. But I want you guys to consider that beautiful, hard, carbonaceous ring that we've been cleaning off the backs of throttle plates for 35 years now. Now, that throttle motor doesn't have an IAC bypass, so as that ring of carbon builds up on the back of the throttle motor, what's its only course of action to fix that? It has to crack open a degree or two. Now, I want you to follow me over here, okay, because I got to see where my little tool is. Okay, think about this. Let's just say my injectors over here, baseline, clean and new car, was at 1.5 milliseconds at idle. Okay, warm idle, unloaded, no headlights, just warm idle, unloaded. Okay, that's where you want to do this test. All right, 1.5 milliseconds. Now, my throttle motor at the same time over here, okay, whoops, throttle motor was at 3% when it was new. Now, I get this car in front of me, it's 60, 70, 50, 80,000 miles, whatever it is. It's got the idle shake, it's got drivability issues, maybe they're complaining of poor fuel economy, okay? And I now look at this throttle motor and it's at 6%. Why? Because as this builds up, okay, as this deposit right here builds up, whoops, there we go. What can it do? All it can do is open, 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 open as that deposit gets worse. Now, here's what I want to ask you guys that's really critical to this diagnostic argument here. We know whether it's carburation, right? Whether you fog it in, it doesn't matter. Carbureted, fuel injected, gas direct injected. Okay, if you move idle air, you also have to move fuel to compensate for it. And what I mean by that is you can't really, there are cars that do it, I'll explain that in a second, but you can't really, whoops, let's see, can't have this at 6%, guys, and have this stay. Oops, sorry. This cannot stay. In other words, if I've moved that throttle motor 3% to compensate for that carbon, those injectors have moved too. In other words, right now, they might be at 1.8 or maybe 2.0 milliseconds at idle. As long as this is high, this is going to stay high, okay? Now let me try to just wrap that one single little argument up in baseline data. If I've got a long-term fuel trim that's adding or subtracting, I've got a throttle motor that's gone from what would be clean at 3% all the way up to 6% because the car's coked up and it hasn't been cleaned every 30,000 miles, right? Now that throttle motor is where it is. If I'm working on a GM car, I'm going to have high pulse width. Now here's the technical argument that gets your mind into how to look for and cure and know you've cured to the best of your ability a poor fuel mileage complaint. No codes. There's no OBD2 code that says vehicles using too much fuel, please check and advise, right? No. Okay. What's going to happen here is the longer that throttle motor keeps cranking open, the injectors are going to keep moving with it on a GM car. On that might be a GM model. On a Ford, you're going to see it act much more like a diesel, and you're going to see air adjustment sides. That fuel trim will stay right where it is. So that's one thing you'll get used to as you go after baseline data is, look, I can know that a Ford GDI is moving the air side variable valve timing in the throttle motor, whereby the GM is moving fuel trim along with these adjustments. All depends on the vehicle, right? And what we're working on. Now, let's go through the rest of this because it's important. I think you guys get the argument here that we have a baseline adjustment on the injectors and the throttle motor that can be correlated before and after cleaning to see that they cleaned up. What's the point here? The point is, if we start those injectors at 1.5 milliseconds on a clean car, the injector count never goes down when we step on the gas, it always goes up. The argument there is, if we're now at 1.8 here, then we're using too much fuel all the way through the operating range of the car. Why? Because the pulse width doesn't go down when we step on the gas. So if it's high at idle, it's high all the way through the operating range of the car. There's your fuel economy complaint that you haven't been able to quantify without some data behind you to prove it. And then what I like about this is you can check the cleanup data afterwards and see that you actually positively affected it. Okay, now the next thing I'm going to look at, so remember, we've got long-term, I see a question or two coming in here, so we're at the end here. We're going to get to you here real quick, okay? We have throttle motor, okay? What I want to be specific, if you're writing notes, is percent open is what we're looking for here. Percent open against the injectors. So we have injector pulse width is one data PID, injector pulse, long-term fuel trim, electronic throttle motor, okay? Then I like to look at spark advance. Okay, now let me explain why spark advance. We've covered the addition of fuel, subtraction of fuel, the fuel trim issues, the math plausibility and intake issues, the big snot of ice cream cone looking carbon sitting on that valve, how it's affecting the tumble and swirl. Now, let's close that argument up and we'll find out where our cursor is, and we'll come down here and we're going to start to grow carbon, not just on the top of the piston, but down here where the rings are sealing to the cylinder walls. As that carbon builds up, what are we essentially doing in here? We're reducing the amount of space, or we're negatively affecting the volumetric efficiency of the engine. Remember, this goes back to a fuel map. X equals 3.5 liters. Now, as this slowly builds up, we no longer have 3.5 liters. What's going to happen as that air gets interrupted and all these deposits are building up exactly as we've shown you today is that the NOx sensor is going to have to step in here and correct for some of that volumetric efficiency issue. Now think about this. If I start getting interruptions in these air and fuel burns, the combustion as we were talking about, what's going to happen? Hot spots and cool spots and combustion. What's that going to lead to? Detonation. What's a knock sensor going to do to control detonation? It's going to retard the ignition timing, folks. Retarded ignition timing equals low power on that car that you can't solve because you don't drive it every day and you don't realize it really does have low power. Spark advance or spark retard, depending on which data PID they give you, is really going to be your best friend for finding that. Go out and whack the throttle and watch what that spark advance does. It's going to tell you a lot about what's sitting here on top of this piston. And finally, that soot deposit, okay? The mixture of oil burning and soot is going to begin to impact carbon into the substrate of the converter. This is a very big argument for a tank additive like a 44K or a ATS tank additive or a WINS or whatever system you use. Very, very big argument for that. Big reason is the more oil that is going across that converter, the more poisoned it gets and the more chance we have of the PO420 and PO430. So the final data PID that I like to look at here down here is our calculated engine load, okay? Because if I had a load that started out at 17% when my car was clean and new, and now I've got a load of 27%, and guys, I see the calculated engine load go way high on idle on these cars that are clogged up like this, okay? So just to review, because I know we're at 2 minutes past 1 o'clock and you guys got to probably get back to work, all right? Long-term fuel trim, number 1. Injector pulse width, number 2. Electronic throttle motor, number 3. Spark advance, number 4. Engine load, number 5. And on modern day cars, I always throw in a 6th because it almost always comes into the equation for diagnostics, and that's going to be variable valve timing data, okay? Now, you take the blend of these 5 data PIDs and you start to evaluate the before and after results as you clean these cars up and you key into some of these issues diagnostically. It will change your diagnostic world. Don't forget, of course, to mix up and get that physical testing transducer activity going on in your diagnostics with these issues. Because guys, I'm telling you, when I throw that waveform in step 2, after I've looked at this data, I'm usually finding my problem in 15, 20 minutes or less. No joke. And it's happening over and over and over again with support calls. We're finding these problems after the tech's banged his head up against the wall for a few hours or a few days trying to figure it out. So that it is what we're talking about is the real deal, guys, when it comes to what we're doing here diagnostically. Now, let me just get my control back here, if I can. I got to get out of this pen mode somehow. Hold on, guys. Fumbling and stumbling again. There we go. All right. Now, let me end the show. We're going to take a couple questions here. There we go. My goodness. All right, hold on, guys. 1 second. The pain will be over with. There we go. All right. Better. Oh my goodness. All right, hold on, please. All right. Somehow I'm stuck here. I'm really sorry, guys. Just give me a second. I'll get through this, I think. Okay. Discard. There we go. My goodness. All right. So, guys, I'm hoping that you were able to just get these written down here. Okay. Another neat one I use is relative compression. Sorry, that was like the worst 2 minutes of pregnant silence ever in a webinar. My apologies. I'm just going to blame the new computer till I'm used to it. And this is what we really need to key in on, as well as that transducer data. So what I'm going to do at this point is I'm going to take a look at our questions here, see what we've got. Let us see. Okay, where is baseline data available at? John, nice to see you here. First of all, thanks for attending. Baseline data, as I was explaining in the beginning, is more, in our case, going to be a learned art form, John, meaning taking readings before and after we do these jobs on the car and gaining an idea for where our baseline should be. Reason for that, John, is obvious. We have, I mean, people are coming in at all kinds of mileages and all kinds of dirty up conditions. So there's no real way. For example, a new car dealership has all the best baseline data available, because all they have to do is take a car on a new car prep, warm up the vehicle, print the data stream, and they've got a perfect, clean, new, beautiful baseline. In our side, in the aftermarket, what I'm going to have to do is I'm going to have to look at a car that's in trouble and record the data, and then clean it up with my fuel injection system cleaner or my induction system cleaner, and then idle the car and pull the data afterwards. Making the comparisons from clean to dirty that way, backwards actually, from the way a new car dealer would do it, is how I've gained my baseline knowledge and data over the years. Hopefully that answers your question, John. Anybody else have a question that you wanted to ask? All right, well, you know, other than my bumbling and stumbling with my new computer, I hope you guys really enjoyed the information today. You know, the biggest thing to remember with this is that putting this thought process, this analysis, this look, this theoretical look, and this mechanical look at a lot of our ghost drivability problems can and will, in fact, guys, help you to get to that answer quickly, more accurately, with less comebacks and with less heating up of the parts can and barrel. So, you know, I can't stress enough to try to take this kind of diagnostic methodology seriously. Start looking at these carbon issues as a root cause right off the bat, rather than parts replacements and or electronic problems. Guys, you can't imagine how many plausibility codes these issues are creating today. So with that said, again, happy holidays. I wish you guys all the best in the new year. Let's hope it's a little less crazy politically and COVID-wise than this year was. But really, thanks for enjoying this with us today. If you have any questions, my email's up on the screen, gsmith@diagnation.com. DiagNation.com is there for any and all of you guys that might need to get in and get a support call done, get some help with the car, get some information, resources, that kind of thing. So with that said, I want to thank you very much for attending the WMDA Lunch and Learn webinar today on deposit and diagnostics. Thank you so much. My name's Gary Smith. I'm going to end the webinar. Have a great one. All right, thanks, John. Thanks for the comments. Thanks. Oh, now one more reminder. Thanks, Swapna, that we have the virtual training conference. You go to the WMDA website, check that out. February 26th through the 28th of this year. And I believe this year we're going to be doing something neat and unique within the virtual training conference, which is, instead of it being all on one day, training day has historically been on one day, on a Saturday. This year we're going to spread it out over 2 or 3 days, I believe. I'm really excited about being a part of that team. Should be really fun to get everybody together and get that training done on February 26th and 28th, virtual training day for WMDA. With that said, guys, again, God bless, happy holidays. Thank you very much for being with me. Take care, man. We'll see you next time.